So again, we're going to locate the asymptotes and other key features of the function. Draw all asymptotes on the graph. Use our graphing calculator to help us plot other key points. So first, our denominator is going to determine the domain. So our denominator, the bottom of the fraction, is x minus 1 doesn't equal 0. And then we're going to add 1 to both sides. When we do, that's going to determine our domain, which is x doesn't equal 1. Now, at a quick glance, we look to see if we can factor up here in the top of our problem, and it just so turns out that we can't. So consequently, because we've got this domain that's x doesn't equal 1, that also means that we have a vertical asymptote at x equals 1.
So anytime you can't factor, the domain is also the...
So why don't we, right now, put in our vertical asymptote, because we know we've got one, at x equals 1. Remember that that line crosses the x-axis. Typically, we write a vertical asymptote with a dotted line. We do not have any removable discontinuity in this problem because there's nothing that cancels out. So again, write none, write not applicable, whatever works for you for that. Then we go to our second column over here, and it says horizontal asymptote. And I know I haven't even typed this into the calculator, and we can in a minute. But if we look at this, so when we're looking for a horizontal asymptote here, what we are going to look at is we're going to look at the degree of the numerator. Well, the highest degree term in the numerator is 2x squared. And the highest degree term in the denominator, the bottom of the fraction, is x, and if you prefer, that's x to the first. So this one qualifies as top heavy. And when we look back to our chart here on the previous screen, the top heavy tells us over here to the far right that we are going to have an oblique or slant asymptote. And a couple things that you don't know at the moment. One is that if you have a horizontal, you don't have an oblique. If you have an oblique, you don't have a horizontal. So once again, since we don't have a horizontal, I'm going to write not applicable. I want to say it one more time. If we have a horizontal, we don't have an oblique. If we have an oblique, we don't have a horizontal. It's either or. So now, how do we figure out how to find our oblique asymptote? It's going to be a y equals. And, well, I don't have enough space. I hope you have better space than me. We're going to go back to an old concept from Algebra 2 called synthetic division. Now, if you like long polynomial division and you want to do long polynomial division, you're welcome to do long polynomial division. But synthetic division works like this. We want to have the top of our fraction in descending order. That means highest degree term first, next highest degree term, then the constant. Same writing in the bottom. And then the way I like to explain it is I like to write an upside down division bar. What's going to go in this upside down division bar is the number in front of the x squared, which is 2. The number in front of the x, which is negative 2. And then we have a negative 1. The 2 in front of the x squared. The negative 2 in front of the x. And the negative 1. When we divide with synthetic division, we change the sign here. It says x minus 1. So we're going to change that to a positive 1. If it were x plus 1, we change it to negative 1. We bring down this term right here. Every single time that happens. Bringing down the 2. And then we're going to multiply. 1 times 2 is 2. Negative 2 plus 2 is 0, and I usually write plus 0, but you can write minus 0. 1 times 0 is 0. Negative 1 plus 0 is negative 1. And what we started with? We started with an x squared, but whenever we divide, our degree decreases by 1. So we started with x squared, so when we finish here, this is going to be x to the first. So in terms of our polynomial, and I'm really sorry I'm squeezing it in, I'll try to use my space better on the next problem. What we have is we have 2x plus 0 minus 1 over x minus 1, which is our remainder. The minus 1 goes over whatever we were dividing by, the x minus 1. And then, though, to come up with the slant asymptote, what we do is we ignore the remainder. We don't need this. And consequently, our oblique asymptote is y equals 2x, if you prefer, plus 0, or just y equals 2x. It doesn't make any difference to me. Now, again, we've done all of this without even looking at the pictures, and I do have them down below, but remember when you graph this, is that our slope is 2 over 1, and our y-intercept is 0, and then I'm going to go up to the right 1, 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 or down to the left 1, 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 down to the left 1. And I actually usually leave it on my paper just like that. I don't connect them for the asymptotes. Traditionally, you see the asymptotes represented with dashed or dotted lines, like that. So there's our asymptotes. But what does the picture really look like? Because we still do need to find the x-intercept and the y-intercept, and that's still giving people some trouble too. So let's pull out our calculator and go to y equals, and I have them all in. So as provided that I typed them in to here correctly, when I press enter, here, when I press graph, we're going to get that picture. And what can be helpful here is we can go to second and table. And typically on your graphing calculator, you start on your calculator with 0, 1. I know it's not on my screen right now, but 0, 1 from the table is going to tell us that our y-intercept is 0, 1. Now, if we look real close here at our picture, back to our picture here, I don't know what these values are right now, and that since I'm making this video here, I should point out what these values I'm talking about. I'm talking about this point right there, which is an x-intercept, and this point right there, which is an x-intercept. But we can figure out what those are, and this is where you really might want to take out your calculator. If you don't know how to find the x-intercept with using your second trace feature or second calculate feature, then talk to your teacher to get some extra help with that. But what we just found is 1.370 and negative 0.370 for our x-intercepts. And what we're going to finish with on this particular problem is we're going to draw the picture. And at the bottom of my screen, I have the table in here so that we can just get a couple of pictures in there, or a couple of points in there. So I think that I'm going to graph -1, -1.5, so -1, -1.5. I'm sorry, my board's a little bit disoriented, and 0, 1. But we end up with something that looks like this. And then on the other side of our vertical asymptote, let's graph 2, 3, and 3, 5.5. So 2, 3, and 3, 5.5. And the nice thing with the graphing calculator is we can see the picture. I'm not super accurate, but I'm pretty good. Not too bad.
I think it's easy.
So that was the first one that we've seen like that. So it might have been a little bit wacky when we're trying to do all of the different types. But let's try this again. And hopefully what you notice first and foremost is that we're going to have to factor the denominator. And our denominator here of x squared minus 9 is going to be x minus 3 times x plus 3. And what we get from that is we can get our domain. And our domain is determined by taking x minus 3 does not equal 0, and x plus 3 does not equal 0. And if you need to, then you add 3 to both sides, and we get the x doesn't equal 3. We subtract 3 from both sides, and we get the x doesn't equal -3. Some students can look at that and go directly to the domain. I'm okay with that. Now, our numerator in this fraction is a 9. Nothing is going to cancel out. And what that means then is that our vertical asymptotes are going to be x equals 3 and x equals -3. And by the way, if you want to use the plus or minus symbol, I am fine with that as well. Thirdly, we did not cancel anything out. And because we did not cancel anything out, we don't have a removable discontinuity. So again, put something in that spot so that I know that you know that there's none that exist. So now, let's look at this function and look at the numerator. When we look at our degrees here to determine our horizontal asymptote, well, the numerator, we have a 9 up here. There is no exponent on there. The degree of the numerator is 0. It's 9x to the 0 if you want to get specific. The denominator, the degree is x squared. And what we see in this particular case is we see that this is going to be a bottom heavy function. And you can look at the top of your page at the chart, but I need to flip back on my screen here. What happens when we have a bottom heavy situation? We have a horizontal at y equals 0. Y equals 0. Once again, if we have a horizontal, we don't have an oblique. If we have an oblique, we don't have a horizontal. So if we have horizontal, so we don't have an oblique. Let's go ahead and go back into our calculator here, and we're going to look at our next picture. And we'll hit graph, and it looks like that. So there's our picture. We can look at the table here, and we see a couple of interesting things like errors in there. But what you might notice here with the errors is what they coincide with. So we've got an error at -3 and we've got an error at +3. When we go back and look at our problem, look what we have here. We've got vertical asymptotes at those points. I should have put them in earlier, but we'll put them in now. -3 and +3. We also just recently found that we have a horizontal asymptote at y = 0. Well, that's here. And then we can use our calculator to get a couple points that may help us to find our y-intercept. And I've got some pictures up here of the table. And we don't have very many nice points in here, but we can make it work. Here, for instance, we've got -2, -1.8. -2, -1.8. We have 0, -1. And I also have +2, -1.8. And not my best picture there. Luckily I have it down here on the screen. But there's part of the graph. And in fact, what's our y-intercept after having graphed that part of it? -1. It's 0, -1. I'm going to change colors here. 0, -1. When we go back here and look at some other values, again, they're not super pretty, but I graphed -4, 1.3. So I'll have to estimate there, and -5.56. But again, look at your screen of your calculator there. Look at something that looks like that. Same thing over here, we've got +4, 1.3. And +5.56. But the picture looks something like that. You can get a little bit of our picture there. Where is this graph going to cross the x-axis? It's not. We have a horizontal asymptote there on the x-axis. We are not going to have an x-intercept. We're becoming a little bit more familiar with these types of problems. Start left on your paper, and maybe that's more for me than for you, because we need to factor the top of this fraction, we need to factor the bottom of this fraction, and then we've got a lot of other little things. Decide whether graphing first is right for you or graphing second is right for you. Clearly it's right for me second. But when we start with this problem, we do need to look at our domain, which is going to be determined from the bottom of our fraction. And it's the difference between two squares. So we get x minus 2 and x plus 2. And we still need to factor the numerator, the top of the fraction, which it's going to take me a couple steps to do that. But before we even get to that fact, remember for the domain, we can take the x minus 2 and set it not equal to 0. And we can take the x plus 2 and set it not equal to 0. And when we add 2 to both sides, we end up with x doesn't equal 2. And when we subtract 2 from both sides, we end up with x doesn't equal negative 2. And if you prefer to use your plus or minus, use your plus or minus. And really, if I get technical, I should say that it's for all real numbers such that x doesn't equal 2 and x doesn't equal negative 2. Now that we have found the domain, we should go back and factor the rest of it, because if we can cancel something out, we're going to have removable discontinuity, and that's going to have an impact on our vertical asymptotes. The first thing that I notice when I look at the numerator is that there's x to the third, and then there's x to the second, and then there's x. There's a greatest common factor of an x. And then we have x squared minus 2x minus 3. So we're going to have to factor again by splitting the middle, which I'm not going to show. And I'm going to go left here to factor, but it's going to be x. And then it's x. 3 and 1 minus plus. And x minus 2. And x plus 2. Well, after we factor completely, what we see is that there's nothing that's going to cancel out. And consequently, that means that our vertical asymptotes are going to be x equals 2 and x equals negative 2. And we're not going to have any removable discontinuity. When we go back here and look, now, let's go back when we approach our asymptotes, or other asymptotes. Our horizontal asymptote, well, what we have in this problem is we have our numerator is x cubed. Our denominator is x squared. We're taking the highest degree of the top of the fraction and the highest degree of the bottom of the fraction. We have to flip our paper over to determine here, but what I see is that the degree is bigger on the top, so it's top heavy. But let's go back and look at our chart to see what we qualify for, then we are top heavy. It's going to be the oblique. It's the farthest to the right. It's an oblique. We're going to write this in slope-intercept form. And the way that we do that is we're going to use synthetic division. And this one is a little bit wacky in terms of the synthetic division. In fact, I'm going to go to the next page just so I don't cram it all in. But again, the problem was h of x equals x cubed minus 2x squared minus 3x divided by x minus 2 times x plus 2. And the way I wrote it, I don't have that top factored right now. But I need it in that format to do synthetic division. And if you think back to synthetic division is very finicky. It only works on specific cases. What I'm going to do here is I'm going to take the number in front of the x cubed, which is the 1, the number in front of the x squared, which is the 2, and then the number in front of the x, which is the 3. And I'm going to divide, first of all, just by the x minus 2. But remember what happens when we divide. We have to change that sign. So I'm going to make that a positive 2. I'm going to carry this down. change the sign up here. I had to pause the video for a minute, so I just need to recap for my benefit, if nothing else. What I just did is I wrote down the function from the previous page, and I wrote the top of the fraction not in factored form because I want to apply synthetic division to it. And the thing is, on this particular problem, in order to use synthetic division, I have to use the factored form on the bottom. So what I've done so far is I put the coefficients of the x cubed and the x squared and the x in our upside down division bar. And then I'm dividing right now by x minus 2, but I need to change the sign of x minus 2, and that's why that black 2 is positive. And we're going to carry the 1 down, which I have the arrow there for, and now I'm going to multiply. 2 times 1 is 2, and negative 2 plus 2 is 0. 2 times 0 is 0. Negative 3 plus 0 is negative 3. So we divided by the x minus 2, and now what's going to happen is we're going to do that division again with our other factor. Because synthetic division only works when you divide in the format of x minus something or x plus something. You can't have x squared. So this time, looking at the x plus 2 this time, so what we're going to divide by is we're going to divide by negative 2, because I changed the sign on the plus 2. Carry down the 1, and now we're going to divide. Negative 2 times 1, sorry, when we're dividing, we're multiplying. Negative 2 times 1 is negative 2. 0 minus 2 is negative 2. Negative 2 times negative 2 is positive 4. Negative 3 plus 4 is 1. And just recall, we started here with x cubed. When we divided the first time, then our polynomial became an x squared term, but we divided again, so when we finished this, now we're down to x to the first degree, and what we're left with now is we're left with 1x minus 2 plus 1 over, if you want to get technical, it's the x squared minus 4. But it doesn't matter that part, because what matters is the 1x minus 2. That's what's going to go back in over here for our oblique asymptote. We don't have a horizontal because we had a top-heavy function. We just used synthetic division, and we came up again with y equals x minus 2. And there's something interesting that you can see when you look at this on the graph. So I'm going to come back over here to the y equals. I'll get rid of our second function, and let's look at our third function here. And we graph it. So it's kind of a wacky picture there. But what we just came up with is we just came up with our slant asymptote. Remember what it was? It was y equals x minus 2. Look at this on the picture. Doesn't make sense when you type it in, and especially with these color graphics, I think that it makes sense in the picture to see that. But that's a personal preference, and I'm going to go ahead and take that out now, because what we want to do is we want to graph that. So we can go to second table to look at this, and we can get some points that we can use here that I have actually back here on my screen. So first and foremost, let's put in our asymptotes of x equals 2. And x equals negative 2. And then our y equals x minus 2. So remember that b is negative 2, and our slope is 1 over 1. Up 1 over 1, up 1 over 1. And downward to the left. So there's our asymptotes. And then again, we can get a couple of points here. I thought that would cover up those, and it didn't. Okay, that doesn't help. So I'm going to slide that back down. But if I start here, let's graph negative 4, negative 7, negative 4, negative 7. And negative 3, negative 7.2. If we look over here at our picture there, we can kind of see, even though I don't have very good points, I actually also graphed negative 3.5, negative 6.9. But we end up with something like that. And again, look back at your screen. Does it seem reasonable? I think so. If we go in between our two vertical asymptotes there that are in blue, we can graph the points negative 1, 0, and 0, 0. Negative 1, 0, 0, 0. And I also graphed the point 1, 1.3. And the middle of our graph looks something like that here. And then off to the right in this picture, if I look down here at the screen, let's graph to point 3, 0. For one of them at least, 3, 0. And let's do 4, 1.67 or so. But we're sketching the graph. It's nice to have a couple of real points on there, but there is a rough picture. And I want to remind you here with the x-intercept and the y-intercept, which we can, in this particular problem, find the complete value on here. But with an x-intercept, our y value in the order pair is always going to be 0. And in a y-intercept, our x value is always going to be 0. And if we look here at the screen, what we see is that we have point 0, 0, which not only is a y-intercept, it's also an x-intercept. But if we look real closely here at the graph, our graph crosses the x-axis more than once. And it happens that it crosses the x-axis at this particular point as well, which is 3, 0. Table 4. Once again, and maybe this time, why don't we start off by graphing it? Just for a little bit of a different perspective. So let's go to our calculator, let's type it in, and maybe for some of you, typing this into the calculator first gives you an idea of what's going to happen. What's going to happen with your asymptotes. And maybe what kind of asymptotes you have. Turning this on. Here's a picture. Looks like that. Remember that the asymptotes are occurring at a gap somewhere in the graph. So maybe you see the gap and maybe you don't. That's when we go back and we look at this problem here, and specifically when we start with our domain, we've got the x squared minus 1. So x squared minus 1, similar to many of our other problems, it's the difference between two squares. And the nice part on this particular problem is that the numerator is already factored. But what we can tell here, just like we were able to tell on some other problems, is that we're going to take x minus 1, set it not equal to 0. Take x plus 1 and set it not equal to 0. If we add 1 to both sides, we get x doesn't equal 1. And then when we subtract 1 from both sides, we get x doesn't equal negative 1. Where's our domain? And when we go back and look a little bit more closely at the problem, what we see is we see that there's an x plus 1 on the top, there's an x plus 1 on the bottom. They are going to cancel out. And because the x plus 1 part of this canceled out, as you look to the right of our two x doesn't equal parts of the problem, the one that canceled out here, we cancel out the x plus 1. That means that at negative 1, we're going to have a removable discontinuity. And our vertical asymptote is only going to be at x equals 1. So again, this is where this x plus 1, that's what canceled out. When we solved that for our domain, we got x doesn't equal negative 1. Because that's the value that canceled out, that's where the removable discontinuity is. And then the one that didn't cancel out, the phone rang in the middle of this video, and I am not even exactly sure what I just said. So I think I left off that we were talking about removable discontinuity, and we figured out that the vertical asymptote is x equals 1, and the removable discontinuity is going to happen at negative 1 when x is negative 1. And the question is, well, how do we find the y value when x is negative 1 for removable discontinuity, which is going to mean that we're going to have a hole in the graph. So remember, with the vertical asymptotes, it's a gap in the graph. With the removable discontinuity, it's going to be a gap in the graph. What we do to find the other value for the removable discontinuity is we take what we did not cancel out. So we've got 4 times x minus 3 divided by x minus 1. We did not cancel out anything there. And what we're going to do is we're going to take the value of negative 1, in this case. We're going to put it back into our function wherever we see x. So it's going to be 4 times negative 1 minus 3 divided by negative 1 minus 1. And when we simplify that value, what we're going to be left with here is 4 times negative 4 divided by negative 2, which is negative 16 divided by negative 2, which is 8. Over here in the graph, we're going to put in, at the point negative 1, 8. We're going to put in open circle right there, and that's supposed to be an open circle. Hard to get that drawn in. We also know that we have a vertical asymptote at x equals 1, so we might put that in at this point in time too. And now let's go back and look, because we have to determine, do we have a horizontal asymptote or do we have an oblique asymptote? And the hard part on this one is that we can see our degree in the bottom. So we need to find the degree in the top of the function, and we need to find the degree in the bottom of the function, n for numerator, d for denominator. And down here in the denominator, it's going to be x squared. But up here at the top, what you have to realize is that we have x times x. It was already in factor form, but x times x is x squared. Now, if you don't see that, what we can do is we can multiply the x plus 1 times the x minus 3. So we get x squared minus 3x plus 1x plus 1x minus 3, which is really x squared minus 2x minus 3. And I don't want to overlook the fact that there's a 4 in front of there. So we end up with 4x squared minus 8x minus 12. So ultimately what happens here is that not only is our degree x squared, but the term is really 4x squared. And what we see now is that we see that the degree on top is 2, the degree on bottom is 2, which means that we have the same degree. And as we look back to our chart here, when we look back at our chart, one more, or two, we're going to have a horizontal asymptote at y equals a over b. Well, our horizontal asymptote then is going to be at y equals 4 over 1. And you can write it as y equals 4. By the way, if we have a horizontal asymptote, then we don't have an oblique. And as we finish this problem here, drawing the picture, we can identify, I hope, what our x-intercept and y-intercepts are. I do want to point out, as I squeeze it in, that an x-intercept always has a y value of 0, and a y-intercept always has an x value of 0. And if we look down here at our table, or we look on our calculator on our table, what I see is that 0, 12 is going to be a y-intercept. And it's not going to show up on our graph because I don't have enough space on my graph there. But again, if we look at our table, we want x values of, or y values of 0 now. And when we look down here, oh, not right there, close, we've got 3, 0, which is our x-intercept. As you look over there at the picture that I have right beside there, and apparently the board's a little bit disoriented, but there's the x-intercept, and then the y-intercept goes off the graph a little bit. But let's see if we can graph a couple of values in here. That'll work for us. Like negative 3, 6, and negative 7, 5. And then on the other side of that, a couple of points that we graph are points like 2, negative 4. Just looking at the your table on your calculator, 3, 0, 5, 2, and even 9, 3. We can get a few points on that one to get that picture. And I'm missing one thing. I realized as I'm finishing up with this graphing here, I did not graph the horizontal asymptote, but we'll finish with that. Y plus 1. I missed here when I graphed this point here because it really should go through that red open circle. I'll try to make it an open circle here at the negative 1, 8 and erase that little part there to make it a little bit more precise of a graph.